Hi everyone, my name is Feng, and my talk is about adaptive shielding via parametric safety proofs. And the QR code is our paper. So for the motivation part, the problem we want to study is that we want to deploy cyber-physical systems in partially unknown environments. We can look at the example first. So there is a train braking control system. So we want the train to stop near the obstacle, but we cannot crash into the obstacle. And there's uncertainty about the track incline. It means that if we intend to apply an acceleration, there is some unknown offsets, and we cannot directly determine it, and we need to measure maybe when we're doing interactions with the environment. So in this case, we have to use learning-enabled controllers, which means we gather information during our interactions with the environment, while we can still ensure the safety of the system. If we do not use learning-enabled controllers, for example, we use totally fixed controllers. In that way, we have to be very conservative because we do not know the environment and the controller cannot update itself. In that case, the controller is overly conservative, and it will sacrifice a lot of the performance. Before we go too deep into this problem, we can revisit static shielding via formal methods. So as a starting point, we can assume that the train braking system, there's no uncertainty. We know the incline. We know our acceleration for sure. So in this case, we can just use a static formula. We prove the core formula here. So the formula is that it means that under a certain initial condition, under any executions of our controller and the environment evolution, the safety condition is always satisfied. So if this formula is proved, then we can just apply the controller defined by the control to guarantee safety during the training and testing. So we can also write it more formally using some formal techniques. So we introduce hybrid programs. So it is expressed in differential dynamic logic. So there are four basic syntax. So we can do assignment, we can check a formula, also we can follow the differential equation. Also we can compose several hybrid programs into a new hybrid program. For example, we can nondeterministically run a hybrid program, or we can use a sequential run. Also there are some loops. So with such DL tools, we can formally write the train braking system. So for simplicity, we assume that during each control interval, the train only has a binary action space. That is, it can accelerate with a given acceleration A or brake with a acceleration minus B. So there are only two choices. And the core part is that we need to find a control. So here the control, it basically means that we can always brake, that is A minus equal to minus B. And if we want to accelerate, we need to check this condition. And this condition, it basically means that we have to check the braking distance under the next control cycle. If the braking distance is large enough, we can accelerate in this control cycle. Once we find such a control, we can just follow the shield derived from it. And in this case, it can guarantee safety both during training and testing. And the safe condition here is that we do not exceed the obstacle, and the planned part is just about we move according to the acceleration we just selected. However, as I just said before, static shielding is not sufficient for partially known environments. So if the environment is not fully known and we only afford to do static shielding, we have to consider the worst case to guarantee safety. So this sacrifices the performance. However, if we want to do adaptive shielding, there is also a lot of challenges. So we need to express the uncertainty in the environment, and we also need to define how we adaptively update our controllers. Also, we need to guarantee safety for sure, and also there's some runtime efficiency considerations. Our solution is that we have a programming language framework, so it is expressive, and the experts can specify adaptive shells. And the adaptive shells, at the beginning, it may be also conservative because we do not know about the environment, but it can become increasingly permissive as we get more information from the environment. So here is the overview part. So this is a programming language framework. So we need human experts. They define the shell specifications in our language, and we have compilers to compile it into proof obligations and also reinforcement learning trainers. So for the proof obligations, these are like offline obligations. We do not need any runtime verification. And for our adaptive shell, so it contains two parts. So the controller monitor, it is just correspond to the control we said before. It will replace unsafe actions by the fallback action. And the inference module, it will update the controller. So here the main difference between our controller and the previous controller is that our controller is parametrized. So there's a parameter controlling its maybe conservativeness, and the inference module updates such parameter in a formal way. And how we update it is that we collect information, that is observations from the interactions with the environment, and we use that information to update the controller. So we can look at about more details about the updates. So additionally, the reinforcement learning agent, it needs to learn an inference policy. It can be learnable or it can be fixed. So the inference policy, it needs to determine the observations. So what observations we are going to use, and how many budget can we use for each observation. So the budget is the significance level. So we consider there are some randomness in the environment. So if we use these observations, we have to leave for some significance level to give some probabilistic bounds. And after the inference policy, it passes information to the inference module, and the inference module will handle the rest of the problem, that is doing sound statistical inference and update the controller parameters. Also, we can look at the training example. So here is an visualization of one episode. So the dots here means the position of the train over time. We can see that it moves closer and closer to the obstacle, and it finally stops near it, but do not crash into it. So the blue color means it chooses to brake, and the red color means it chooses to accelerate. And the vertical lines are the braking distance if it chooses acceleration this time. There are some green circles. A green circle means that it spends some budget to do statistical inference. In this way, it can update its controller, and the controller can be less conservative. And the effect of such updates are shown in green vertical lines. So we can see that once we perform an statistical inference, the breaking distance will be reduced. And now we can look at the shell specifications corresponding to such problem. Here are some assumptions. We assume that the effect of the unknown incline is an unknown function f. It depends on the current position, and we assume it is bounded and k-Lipschitz. And then we choose to use a parameter f bar to estimate its upper bound. And for the controller part, the controller is dependent on the f bar, and but the design is kind of similar to the static shielding case. That is, we can only accelerate when certain conditions are correct. And also the environment ensures that the train can always stop, considering the worst case scenario. And there are also relevant proof applications. Yeah. And also there are some inference part. So we get noisy observations of fx. So there's a Gaussian noise. And the inference part, the user defines how we do inference. So we use the boundedness condition, the Lipschitz condition, and also the observations omega to update our estimates of the upper bound. And also there are some relevant proof obligations to check whether these inference strategies, they are sound. So totally there are these proof obligations, and most of them can be checked automatically, and only one, the red one, we have to assist the automatic provers. So there are some results. So we can see the adaptive is our method. So relevant regarding the unshielded case, we do not crash during training and testing, but we also do not sacrifice the return. So we are very close to the unshielded case. And for the non-adaptive, that is static shielding, in that case, the return is sacrificed. And also the overhead is very low. It is within 15%. So that is the conclusion. We have a programming language framework, and we can specify the specifications. And are there any problems?
Thank you. Other questions? So can you say something about the other use cases that you looked at?
Yeah, although we do not present it here, we have a robot like crossing the river, so that is also a use case. So the robot it needs to cross the river over a bridge, but it doesn't know where the bridge is. So it needs to collect information about the position of the bridge, and then it can successfully cross the bridge.
But there was still a zero possibility that you would crash after training, right? Did I get that right? So in the last column?
Yeah, there's zero possibility, but the probability can be specified before training.
I see. Okay.
Yeah.
Well, thank you again.
Thank you.